So some of you might have been thinking about like, why are we learning about these serious things? Why do I care if this infinite sum converges or diverges? Why do I care about this? What are we going to use this for? Like, what's the purpose? So one of the purpose is so that we can construct these things which are called Taylor polynomials. And the reason we're going to do that is because one of the main ideas about calculus is that we can use functions to approximate other functions that are nearby, right? So think of that tangent line approximation value, right? Local linearization, we've been doing those approximations this year. So if you think back historically, before we had computers or calculators, you really couldn't evaluate a natural log, an e to the x, a trig function, without using a pre-known table of values, right? You couldn't just say like, I want to know what the natural log of 3 is, right? You'd have to consult a table, and you'd have to rely on the accuracy of that. So polynomial functions, however, are pretty, I'm not going to say easy, but they are manageable to approximate by hand. You can plug in a value to a polynomial, you can do all of those hard computations, right? You can do all the powers by hand, you can do adding and subtracting by hand. So we can use polynomial functions to approximate other elementary functions like sine, cosine, natural log, e to the x, all of those core functions in math. We can approximate with polynomials. So before we get into that, we're going to kind of review tangent line approximations. So we're going to find the equation of the tangent line to y equals sine of x. I'm going to actually change this to be f of x. Right? So if I want to find the tangent line at x equaling 0, I need two things. I need a slope, which is really the derivative. So I'll label it as f prime of x. And f prime of x, derivative of sine, is of course cosine of x. And then I need a point. Right, so my x coordinate is 0 because I was given that we're evaluating at x equaling 0. And then my f of 0 is sine of 0, which is 0. So when I go to construct my tangent line, I'm going to use point-slope format because I think that's most useful. It's the easiest, in my opinion, to use. Right, so there's my point-slope formula, so I'm just going to plug in what I have. So y minus 0 equals my, but I never actually found my slope of 1, of 0, rather. I jumped ahead to the answer, right? Cosine of 0 is 1. So my slope is 1, and my x0, my x1 value is also 0. So my tangent line is actually y equals x. So the second part of this question is we're going to use this to approximate the value of sine of 0.2. So 0.2 is not far away from x equaling 0, so this is not an unreasonable approximation, right? So our sine of 0.2, right, that's going to be approximately equal to our tangent line evaluated at 0.2. But since our tangent line is just y equals x, we can say that sine of 0.2 is approximately 0.2. And so now if we want to determine if this is an over or an underestimate, right, we're going to look at that second derivative. So second derivative, right, the derivative of cosine is negative sine of x. And so now we want to think about what is the sign of this second derivative on the interval containing x of 0.2. So we know that sine is normally positive in the first quadrant, so negative sine would then be negative. So we can say for that f double prime of x is going to be less than 0 for x between 0 and pi over 2, and x equaling 0.2 is definitely an element of that interval. Right. So because we have a negative second derivative, we're concave down, that means our tangent line is going to lie above the curve. So this is going to be an overestimate. Right. So if you need that written out, since f double prime of x is less than 0, our tangent line is above the curve. Right, so this is an overestimate. Okay, so when we've been finding tangent lines and using them to approximate values this whole year, we've actually been finding what's called a first-degree Taylor polynomial. So we can find other degrees of Taylor polynomials, and the more degrees we have, typically the better approximation we're going to get. So Taylor polynomials with higher degrees are going to be used to obtain increasingly better approximations of non-polynomial functions within a certain radius from a center of approximation, which we call x equaling c. Right, so that x equaling c is the value that we use to create the polynomial. So in the first degree tangent line problem that we just did, our x equaling c is x equaling 0. Right, and so our Taylor polynomial approximations are only going to be accurate within a certain window. So I'm going to have to kind of like jerry-rig a document camera setup so you can see my, excuse that noise, see my graphing calculator here. So I'm going to pull that up on my computer, kind of just use the camera on my iPad for that. But you have the instructions down here on your screen. We're going to look at graphing y1 is sine of x on our graphing calculator. We're going to use that window. And then in y2, we're going to successively add a term to each graph. So for our first y of 2, right, we're just going to type in y equaling x, which is the tangent line that we just found. And then we're going to do this a couple of times, right? We have 1, 2, 3, and 4. I might actually do it all separate, kind of like actually no, we're going to kind of see what happens. Let me pull up my camera and just prop you guys so you can see my screen. Welcome to my little homemade office here. Okay, so we got, there's my calculator. So I'm going to go to y equals. I'm first going to check my mode. I am in fact in radian mode, so we're good. Go back to y equals. So in y1, we're going to put sine of x. And then I'm going to put in our tangent line approximation first. So we're going to go, that was y equals x, and then we're going to adjust our window. And if I recall, just flipping back to this a little bit, we got -9 to 9 and -4 to 4. Okay. Yeah. Okay, we got -9. Oh, I used the minus key. I forgot I am using, there we go. Got to use my actual keyboard here. Okay, so we're going to go to 9, and then we got -4 to 4. Okay, so we're going to hit graph. Okay, so there's our sine, there's our tangent line approximation. So we can see that like around x equaling 0, I'm going to actually zoom in even a little further here. But why don't we go from -2 to 2? Let's just make it a little tighter. Right, we can see that it is pretty close around here, right? That red and blue curve look very close to each other. So then I'm going to actually go back, and in y3 now, I'm going to put the next term in. So we have x minus, and then our next term was x cubed over 3 factorial. So I'm going to create a fraction by doing alpha y equals, and then I've got x cubed over 3 factorial. Remember, factorial is under math. You're going to go over to probability, and then it's option number 4. Then I'm going to go back to my graph. Right, so we can see now the black curve is our newest approximation, and now this one's even closer to looking like sine of x over that window that we have set up here. Okay, so now what if I go through, and I'm going to be smart here, in y4, I'm just taking what I have in y3, so I'm going to use my variables, go over to y variables function, and I'm going to use y3, and then I'm just going to add on that next term, which was alpha y equals to make a fraction, right, and our next term is x to the 5th over 5 factorial. And then 5 factorial. There we go. Going back to our graph. Oh, look, that curve is even closer now, right? It's almost entirely on top of the blue curve, which is our original sine of x curve. And then if we do the same thing one more time, I'm going to put this in y5. I'm going to use what I have in y4 since I'm just adding on a term each time. And now our next term is that fraction x to the 7th power. over 7 factorial. Right, so it should look like that. Go back to our graph, and now look, right, that green curve almost entirely covers our y1 curve, which is that sine of x. So over this interval, it looks really good, and if we actually go back to that original window that I said, I'm just going to change the x's here since we know that sine only goes from -1 to +1, right, we can see even further out what is happening. Right, so as we added on more terms, our window here gets wider and wider for where the curve looks like it's directly on top of the sine of x curve, which is pretty great. So switching back to our notes here, right, we know that, if I could find my Apple Pen, there we go. We know that y1 of 0 is just, this is just sine of 0. Oh no, my pen is not working right now. Give me 1 second. Okay. Right, that's just sine of 0, which is equal to 0. And then we know that y1 of 2 is the actual value of sine of 0.2, which if we use our calculators, I'm going to quick set my calculator to be on table set for ask. Right, so my actual value, according to this, is 0.1987. That's my actual, my approximation, of course, for sine of 0.2. And now I'm going to pull this up on my screen again. I'm just going to hold it this time, so it might be a little shaky. So we know that looking at this, each one of these is a successive approximation, and look, we're getting really close to being the same value. And looking over, I can kind of scroll over and you can see the decimal approximations. Okay, so this one's not too great, but this one's getting pretty close. And then they're pretty close all the way across, so we're getting a little bit more accurate each time. Right, so I'm just going to write C calculator because it changes each time, except for the fact that on our calculators we can actually say no matter what, do this again. If I go to my calculator and I can type in 0, they all have a y and x intercept at 0, right? They all go through that point, which is nice. Right, and then the approximations get a little bit better every time we add in a different term. So all we're going to do to kind of finish this video out today is talk about what our definitions are. So we have 2 different types of polynomials that we're going to talk about, Taylor polynomials and Maclaurin polynomials. So these are named after 2 different mathematicians, and they're very similar to each other. So Taylor polynomials are kind of more general. So the definition for an nth degree Taylor polynomial is if f has n derivatives, at x equaling c. Right, so that could be any number of derivatives. You could have 3, 4, 5, as many as you need. So this is going to be really great for functions like sine, cosine, tangent, natural log, e to the x, where you can just like keep taking derivatives forever and ever, and they never zero themselves out. So if f has n derivatives at some x equaling c value, then the polynomial Pn of x, written like this, equaling f of c plus the first derivative of c times the quantity x minus c plus the second derivative of c divided by 2 factorial times x minus c squared plus the third derivative of c divided by 3 factorial times x minus c cubed, plus, hopefully you see the pattern developing, plus dot 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 out to the nth derivative of c. Remember, we use that parenthesis around the exponent on f to indicate that's the nth derivative, over n factorial times x minus c raised to the nth power. That's called the nth degree Taylor polynomial. So it's called the nth degree Taylor polynomial for that particular function f at x equaling c, which we call the center of the polynomial. That's like your center of approximation. So Maclaurin is basically the same thing. And whoa, my spacing was not great there, but that's fine. I can fix it later. So a Maclaurin polynomial is a Taylor polynomial where c is equal to 0. So Maclaurin polynomial definition is if c is equal to 0, then the Pn of x polynomial equaling f of 0 plus f prime of 0 times x plus the second derivative at 0 over 2 factorial times x squared plus the third derivative at 0 divided by 3 factorial times x cubed plus all the way out to whatever the n value is. So we have the nth derivative evaluated at 0 divided by n factorial times x of n. Is called the nth degree Maclaurin polynomial for f. So Maclaurin polynomial is just a special case of a Taylor polynomial where the center of the polynomial is around x equaling 0. So it's kind of like that, like all squares are rectangles.